Inductive definitions and structural induction. For any natural number n, the successor of n is just n plus 1. For instance, the successor of 5 is 6. Natural numbers can be constructed from 0 by repeated applications of successor. To prove that every natural number has a property p, one can use mathematical induction. It turns out that sets of other mathematical objects can be defined by repeated applications of some constructs to certain base objects. Whenever we take this approach, we are using so-called inductive definitions. To prove that every object in a set constructed via an inductive definition has a property p, one can use so-called structural induction. So structural induction is a simple generalization of mathematical induction as you know it for natural numbers. Here is an example of an inductive definition. Let prop be a set of propositional symbols. For instance, prop could be the set containing symbols p, q, and r. We'll be using the symbols to write propositional formulas. The definition tells us what is meant by the set of propositional formulas over prop. The set will be denoted form of prop, and it is defined as follows. The symbols true and false belong to form of prop. So each of these symbols is a formula over prop. If p is a propositional symbol, then p itself is a formula over prop. If a is a formula over prop, then you can write the negation symbol in front of it, and the string obtained this way is a formula over prop. If a and b are formulas over prop, then you can write a and b with the conjunction symbol in between and with parentheses around, and the resulting expression is a formula over prop. The same holds for this string, which involves the disjunction symbol, and this one, which involves the implication symbol. And finally, we say that nothing belongs to formulas over prop unless it can be constructed using the preceding rules. In this definition, points 1 and 2 are base clauses. 3 and 4 are called inductive clauses. In the case of inductive clauses, we take a certain member of the set we are constructing, and we are using this member A to construct a new member, and we insist that the newly constructed member belongs to the set as well. The same is visible in point 4. We take A and B, we construct some new items using A and B, and we insist that they belong in the set. Finally, we have a restriction clause. And soon we will be proving a proposition about the set form of prop. For the purpose of this proof, please notice that formulas involving conjunction, disjunction, and implication involve parentheses. This is not the case for negation. Proposition: let prop be a set of propositional symbols. We claim that every formula X from form of prop contains equal number of left and right parentheses. The proof will be by structural induction. Similarly, as in the case of mathematical induction, we have base cases and inductive cases. With mathematical induction, the base case concerns the number 0, and inductive case is concerned with transitioning from n to n plus 1. Assuming that n has the property in question, we want to prove that n plus 1 has the same property. In the case of structural induction, the base cases will correspond to the base cases in the inductive definition of form of prop, and inductive cases will concern to the inductive clauses from the definition of form of prop. So the first base case: if X is the truth constant true, then it has equal numbers of left and right parentheses, namely 0. If X is a truth constant false, again we have equal number of left and right parentheses, namely 0. The next base case: if X is a propositional symbol, then P is a formula according to our definition, and clearly it has equal numbers of left and right parentheses. Now an inductive case: if X is of the form negation A for some A from formulas of prop. By inductive hypothesis, A has equal number of left and right parentheses. When we add the negation symbol, we are not changing the numbers of left and right parentheses. So the formula X, formed this way, has equal number of left and right parentheses. Another inductive case: X is of the form A and B in parentheses for some, and this happens for some A and B which are in this set. By inductive hypothesis, A has an equal number of left and right parentheses. Let's call this number M. Similarly, B has equal numbers of left and right parentheses. Let's call this number N. When we form A and B in parentheses, we see that it must contain M plus N plus 1 left parentheses. The additional 1 is because we added the left parentheses in front of the formula. And we also see that it has the same number of right parentheses, and in this case plus 1 corresponds to this parenthesis. There are similar inductive cases for disjunction and implication. Once all these inductive cases are considered, our proof is complete. To make sure that the idea of structural induction is clear, I propose the following exercise. Prove that for every A from the formulas over prop, if A doesn't involve the truth constants, then the number of left parentheses in A is 1 less than the number of occurrences of propositional symbols in A. You can pause the video, copy the exercise, and I encourage you to solve it. Here is another definition by here's another inductive definition. Let A be a propositional formula. We are defining the concept of we are defining the set of subformulas of A. This will be denoted subformulas of A written this way. First, A itself is a subformula of A. If B and C, I should say, if the expression B and C in parentheses is a subformula of A, then its components B and C are subformulas of A. So I mean B is a subformula of A, and also C is a subformula of A. Similarly, for a formula of the form B or C, and B implies C. Next, if an expression of the form negation B is a subformula of A, then B is a subformula of A. The restriction clause: nothing belongs to subformulas of A unless it can be constructed using the preceding rules. You recognize the base clauses and inductive clauses. And to make sure that this definition is clear, I propose an exercise. Consider this formula. Now use the definition to find the set of subformulas of A. Again, pause the video and copy the exercise, and then try to solve it.